Dear friends, now we are going to deal with Maxwell's equations for time varying fields. We have already seen the Maxwell's equation for static electric fields. So we know that with slight modifications we can derive the Maxwell's equations for time varying field. First Maxwell's equation is Gauss's law, which is exactly same as that of the static field. So Gauss's law states that the total electric flux is equal to the charge enclosed. So you can see surface integral d dot ds is equal to the flux and charge enclosed is given by volume integral rho v dv. Applying divergence theorem to surface integral d dot ds, you get surface integral d dot ds is equal to del dot d dv. Okay, so comparing these two equations, equations 1 and 2, you can write it as surface integral d dot ds is equal to rho v dv. Applying divergence theorem, you can write it as del dot d dv is equal to rho v dv. So this equation, equation number 4, is known as the integral form of Maxwell's first equation, and this del dot d dv is equal to rho v is a differential form of Maxwell's first equation. Coming to the second equation, it is based on the Ampere's circuit law. We know that the closed loop integral, line integral h dot dl is equal to I enclosed. But what is I enclosed? It is surface integral j dot ds. Okay, so line integral h dot dl is equal to surface integral j dot ds. Then applying Stokes theorem to the LHS, that is, you can write it as surface integral del cross h ds is equal to surface integral j dot ds. This is known as the integral form of Maxwell's second equation. Comparing the coefficients, you get del cross h is equal to j, which is the differential form of Maxwell's second equation. This was applicable for static fields. Over to time varying fields, we have slight modifications to be made. So we are applying the identity divergence of curl of a vector is equal to 0 to del cross h. So you get del dot del cross h is equal to 0 or del dot j is equal to 0. And also from continuity equation, we know del dot j is equal to minus dou rho v by dou t. So you can see there is some incompatibility between these two equations. So we have to introduce a new term jd, which is known as displacement current density, into the equation of del cross h. So now del cross h becomes j plus jd. This term is introduced so as to minimize the incompatibility between equations 9 and 10. So now again this identity becomes del dot del cross h is equal to del dot j plus del dot jd is equal to 0. Okay, so now equating, you get del dot jd plus del dot j is equal to 0, or del dot jd will be minus del dot j. Now what is del dot j? From continuity equation, del dot j is minus dou rho v by dou t. So minus of minus dou rho v by dou t, or you get dou rho v by dou t. Now from Gauss's law, we know del dot d is equal to rho v. So you can substitute that. So dou by dou t of del dot d is equal to del dot dou d by dou t. So you get what? jd is equal to dou d by dou t. So this displacement current density is having a formula dou d by dou t. Okay. So this line integral h dot dl, you can write it as surface integral of j plus jd. Instead of jd, you can substitute dou d by dou t into ds. So this is a modified integral form of Maxwell's second equation. Similarly, del cross h is nothing but j plus jd, or you can write it as j plus dou d by dou t. This is modified differential form of Maxwell's equations for time varying fields. Equation, it is based on Faraday's law. For static electric fields, we have derived that